Hello students, welcome to the class. So today we will do the part 9 of the chapter chemical bonding and molecular structure, in which we will cover the section 4.9. This is the disclaimer. So our today's objective would be to describe the molecular orbital theory. So we'll start with this objective, right? So we'll discuss the basics of all, basics include in this topic, and about the application part if I tell, so that will be covered in tomorrow's class. So today's focus will be on the basics of this molecular orbital theory. If I specify it according to the NCERT, then the first NCERT section that we will cover would be molecular orbital theory, which is 4.7. Then the formation of molecular orbitals, which is done with the help of the linear combination of atomic orbitals, section 4.7.1. Further, we have the conditions for the combination of the atomic orbitals, types of molecular orbitals, and lastly, energy level diagram and molecular behavior. So overall, we will cover up to section 4.7.5, which includes the molecular behavior determined for molecular orbitals configuration. So let us begin the discussion of the molecular orbital theory. So what is molecular orbital theory? What is the basis of it? It is the theory which describes the electronic structure of molecules. In the previous class, we have seen that how the electronic structure of atom is being produced. Okay, so we have seen this in the theory classes of the atomic structure. Now, molecular orbital theory, it is focused upon the electronic structure of not the individual atoms, but the molecule itself. And in this process, MOT takes the atomic orbitals and combine them to form the molecular orbital. Got it? So, what would be the features of this molecular orbitals? If I write the silent feature of this molecular orbitals, then the first and the most important point is that the molecular orbitals are formed from the combination of the atomic orbitals. In the previous class, when we are talking about the hybridization, there also we said a similar thing. In the hybridization theory, what we did, we intermixed the atomic orbitals and produced the molecular orbital and produced the hybridized orbital. In the molecular orbital theory, we are mixing the atomic orbitals and here we are forming the so-called molecular orbitals. Important part and the important difference in these two is that in the case of hybridization, I told you that you have to only combine the atomic orbitals present in the valence shell, right? But in the case of this molecular orbital, your inner core orbitals will also participate in the bonding. Okay, so whole of the atom will participate in the bonding, not the valence shell only. So this is the basic difference that differentiates the molecular orbital theory from every other theory that you have dealt till now. In every theory, you will see that the valence shell were considered to be the only participating shell in your formation of bond. But molecular orbital theory took it to a different level and said that no, not only the valence shell, but the inner core will also be involved in this mixing. And after mixing, we will get a new set of orbitals called as molecular orbitals. I hope you got the idea. It's very important to understand this. Now, if I try to differentiate between the atomic orbitals and molecular orbitals, then the main points of differences would be according to this tabular form. First of all, your molecular orbital is associated with more than one nuclei. Of course, it is true because in the case of a single atom where only one nucleus is present, it is observed that your overall atomic orbital is experiencing force due to that single nucleus. But in the case of molecule, we have multiple nuclei. Suppose you take H2O. you have the nucleus of hydrogen, you have the nucleus of two oxygen. So the orbitals present in the molecule or the molecular orbitals will experience the force due to each of these nuclei, right? So this is very, very important to understand. Next, what about the location? So of course, in the case of atoms, the electrons are on the individual atoms. Therefore, your atomic orbitals are also on the individual atoms, where in case of the molecular orbital, the location is in the molecule. So it's obvious. Now let us talk about the formation. If I talk about the atomic orbitals, they are intrinsic to the atom, right? So we don't need to build it up. It is already present in the case of atom. But in the case of molecular orbital, their formation is taking place as a result of combination of the individual atomic orbitals from which the molecule is made. Okay. And lastly, what about the electron? So same thing. Your electron of the atomic orbitals will be around one nucleus, whereas in this case, in case of molecular orbital, the electrons will be delocalized over multiple nuclei depending upon the atomicity of your molecule. So suppose it is H2O. So 3 is the atomicity. So the electron of H2O will be delocalized over 3 nuclei. I hope this point is clear to you. It's very important to understand the difference between two. Now, if you know that your combination is doing the work of creating the molecular orbital and the combination of atomic orbital, and the new molecular orbital are being affected by both the nuclei, or I would say more than 2 nuclei of the atoms of molecule, then we can move further. So our next point is the number of molecular orbital is equal to the number of combining of atomic orbital. Now this point is similar to your case of hybridization. There also we told, okay, that the number of hybridized orbital formed is equals to the number of atomic orbitals combining. Same point here, the number of molecular orbitals formed will be equal to the number of combining atomic orbitals. So I am trying to point out the difference and the similarities between our previous theories and our modern current theory, which is very accurate in explaining almost all of the molecules. Now let us move on to the second slide. So what is our next feature? Our next feature is molecular orbital. Unlike our hybridization, where the hybridized orbital have same energy. Okay, so if you remember, we said that the number of molecular orbital formed is equals to the number of atomic orbital participating. So that was the similarity, but the formed molecular orbital will not have the same energy like the case of hybridized orbital. Here, the molecular orbital will have different energies with respect to each other. Now, two kind of molecular orbitals are possible. First is bonding molecular orbital, which will have a lower energy and a greater stability. And second type is the anti-bonding molecular orbital. So there is one important point here. So I have not mentioned it here because it is not there in your syllabus. But when you will move to a complex molecule, you will notice a third type of molecular orbital, which is called as non-bonding molecular orbital. But for now, for your class 12th, it is more than enough to know that two molecular orbitals are possible. Bonding and anti-bonding. Bonding will have lower energy, greater stability. Anti-bonding will have higher energy and lower stability. Now, since your atomic orbitals were having the electron density, same can be said about the molecular orbital, and same can be said about the hybridized orbital as well. Here also, your orbitals of molecule will have electron density around a group of nuclei. So it is basically what? It is a electron density which is creating your molecular orbital, and there the probability of finding an electron is really, really high. Next, the most important point. So you got your molecular orbital. After combining the atomic orbital, you know that their energies will be different. Okay. And it is seen that the electrons are filled always in those molecular orbital according to the theories of atomic structure that we have seen. What are those theories? First is Aufbau principle, which says that the orbitals with the lower energy will be filled first, and then will be the chance for the orbitals with higher energy. So as simple as I can say that orbitals are filled in the increasing order of energy. So this is Aufbau principle. Second is Pauli exclusion principle, which says that no two orbitals or no two electrons can have the same set of 4 quantum numbers. Now, instead of writing that complex language, I have given you a simple uh, outcome of that, which says that no two electrons in the same orbital can have same spin. Okay, so like your atomic orbital, here also you will fill the orbitals, molecular orbitals, with 2 electrons with opposite spin. And last and the most important one, that you will only fill the molecular orbital within the same energy after you are putting up single electron in each of the molecular orbital. So we know that suppose your 2p is there, right? So we have seen in the case of atomic orbital. So first we will fill the 2px singly, 2py, 2pz, and then we will start to pair it up. Here also, once you are given a set of degenerate molecular orbital which have the same energy, then in that case you will first of all fill each of this degenerate molecular orbital singly, and then you will start to pair it up. It's very simple. We will see the example and I hope you will understand it very easily. Now, let us move on to the formation, to the process, how this combination of atomic orbital is happening. To understand that, you have to understand this very important concept of linear combination of atomic orbital. Now, what is the meaning of this phrase here? Linear means in a single line, and combination means combining. So whenever you take atomic orbitals, move both of them in opposite direction but in a single line, and after they collide, or you can say they combine, not collide, they combine, they will give you a set of molecular orbital, as simple as that. So this is the most simplest way you can think it of. Okay, now let us try to understand that why do we need this linear combination of atomic orbitals. That's the most important question. So we know that if you are talking about the single individual atom, then in that case your atomic orbital was there, right? And this was expressed in the form of wave function. Once you got the wave function, you got your atomic orbital, you got your electron density. Okay, it was simple in the case of your single atom, or you can say individual atoms. Now, why is the wave function important? Because it is giving you the amplitude of the electron wave, which is probably the probability of your electron. But as soon as you move to multiple nucleus, not nucleus, multiple nuclei, then your problem becomes difficult. So to get this amplitude, so we will not go into the actual process. You will only try to understand that why it's important to get this LCAO, which is linear combination of atomic orbital. Now, if I take a single atom and try to know its position of atomic orbital, then we need to solve the wave function, because the amplitude of the wave function gives you the probability. Amplitude means how high the wave is going. So you can see, imagine it in that way. Now, actually, it is not so, but for your convenience, you can take it in this way, that how high the wave is going, that will give you your probability of electron. Higher is the wave, greater is the probability. So you need to solve the equation for a single electron, or you can say for a single nucleus from the given equation. But this is easier in case of single nucleus. But as soon as you move to more than one electron, first of all, and more than one nucleus. So you are increasing the electron and increasing the nucleus as well. Now the problem is very complex. So you couldn't solve it for more than one type of electron. We have seen it. That for more than one electron, it was nearly impossible to solve. We only applied your quantum theory to hydrogen-like atom. Okay. But when you have more than one electron, it's very difficult to solve it. So what do? We use the linear combination of atomic orbital rather than solving this complex equation. So this is just for your information and you should know it. Not in a detailed manner, I would say, but at least you should know it that there is a wave function which need to be solved to get the position of electron. And the case of single electron containing species, it is easier to do so. But when we increase the number of electron plus the nucleus, this problem becomes very complex, and therefore we need this linear combination of atomic orbital. I hope you got my point. Okay. Now, if you are thinking about this equation, then I would not suggest you to go much deeper into it because it's quite complex. But for your simple understanding, I would try to explain it in a simplistic manner. So the manner would be like this. Suppose you want to differentiate something, right? So you take the differentiation operator. So here your differentiation part is the operator part. And it is acting on a function and giving the differentiated thing. Okay. Similarly, your H is a Hamiltonian operator. And what is the function of this operator? It acts on a wave function and gives the energy related to the wave function. Now, if you know the energy of the wave function, you are knowing the energy of the electron because your wave function is relating it to your electron directly. So that's the simple idea behind the Hamiltonian. Now, there is a complex part regarding all of this. We'll not go into that. So for now, you can think of it in a simple way that your Hamiltonian is giving the energy of the wave function, or you can say energy of the electron. If you are not having the energy of the electron, you won't be able to describe anything about it. It's the most important part in our structure of any small entity like your molecule, ions, atoms. Now coming back to our discussion, now let us try to understand that what is this linear combination of atomic orbital. So let us now move to linear combination of atomic orbital. This was mainly brought into the picture of molecular orbital to solve the problem of solving the multi-electron system Schrodinger equation. Okay. And what it says that you can think of combining the atomic orbitals in a very simple manner. Suppose we have a hydrogen molecule. It is made up of two atoms, A and B. Now your hydrogen atom, two hydrogen atom are forming a homonuclear diatomic type of molecule. Why homonuclear? Means same type of atoms are there which are combining to form the molecule. So we are calling it as homonuclear diatomic. Now what is happening in this formation? Your hydrogen atom has one electron in the 1s orbital. We know that. Now what will happen? Your atomic orbitals of this atom represent the wave functions psi A and psi B. Okay. So in the linear combination of atomic orbital, we will do two things. We have two conditions. Okay. So psi can be equals to psi A plus psi B, or it can be equals to psi A minus psi B. You got it? Again, two things are there, very important. First of all, there can be two operations. First operation can be the positive adding, which is psi A plus psi B. So this is the first linear combination. Okay. And there can be the another linear combination, which is subtracting both of this. Now, I think you got the linear combination right. If not, you can think of it in a much simpler way. Suppose you take two numbers, 5 and 6. You are told to give the linear combination that are possible for these two numbers. What you will give? 5 plus 6, 5 minus 6. As simple as that. Same thing is being applied here, but in apart from integer, we are applying into the atomic orbital. Okay. Now let us move further. Now we will move on to the two types of molecular orbitals that are formed. We have seen that molecular orbitals are formed by the combination of the psi A and psi B. So combination can be either positive one or either can be negative one. Now what is the result of the positive one and what is the result of the negative one? We will see on to that. So first of all, we will talk about the positive one. If you are adding psi A and psi B, you will get a constructive combination. And what is the meaning of constructive combination? So you must have studied this thing in the case of say constructive interference. So like you can relate this here in the same fashion. Okay, so you are adding these two wave function such that there is a bonding condition. Okay, there is a bonding condition occurring here. So in case of the bonding condition, you will add these two and that will result in a bonding molecular orbital. So you can see it here. Psi A plus psi B is giving you a lower atomic orbital, molecular orbital. At the same time, you are getting a molecular orbital of a higher energy as well. But the important point to notice here is that you are getting two types of molecular orbital. Okay. First is due to the addition and second is due to the subtraction. And the number of molecular orbitals formed is equals to the atomic orbitals that are combined. So psi A represents the first atomic orbital, psi B represents the second atomic orbital. After combination of this, you are getting two types of molecular orbital. First is the bonding one, which is psi A plus psi B, which is written here. And second is the psi A minus psi B. We'll talk about this also. And how it is formed? It is formed by the constructive. So why I'm saying it constructive? Because after the formation of this molecular orbital, your energy is decreasing. So you are stabilizing the molecule in a way. So we are calling it as constructive interference. Now, as a result of this constructive interference, three things will happen. First, your electron density will increase between the nuclei. And this is the reason your energy is going down. Why? Once you increase the electron between the two nuclei, then two things will happen. First of all, if there are no electrons between two nuclei, then there will be no shield between these two and they will repel each other. Okay, so this is the first thing. Second thing, now on introducing this electron, what are you doing? You are increasing the attractive force. So your electrons are now between two nuclei. So the attractive force is acting on these electrons in a way. So you are removing the repulsion force by introducing electrons between two nucleus, and you are increasing the attractive force by introducing the electron between the two nuclei. I hope you got the point that why the stability is increased and why it is called as constructive interference. As I said, because of this, the repulsion will be decreased down in the case of two nuclei, and the energy of each of this individual atomic orbital will go down. Overall, the molecule will get stabilized. So I hope you got the idea of bonding molecular orbital. What is happening? You have two molecular orbital. They are doing a constructive interference. So we are adding the wave function of the two atomic orbitals, and we are getting an orbital which is of a lower energy. Why a lower energy? Because upon adding it constructively, you are increasing the electron density between two nuclei, which is reducing the repulsion and also increasing the attraction force. So your molecule is getting stabilized. Now we will move on to the next type of molecular orbital. which is anti-bonding molecular orbital. Now, the opposite sign, which is the negative sign, is the responsible one, which is creating this anti-bonding molecular orbital, which is represented by sigma star. In the case of hydrogen, okay, because if you take two hydrogen, they will form only one type of bond, which is sigma and sigma star. So sigma stands for bonding case and sigma star stands for the anti-bonding case. Now, if you look at this diagram, you can see the sigma star as well represented here. It is having a higher energy than psi A and psi B, and also a higher energy than the sigma itself. Okay. So this is very important to understand, and it's very simple to understand this thing in terms of hydrogen atom. So I've taken this simple molecule due to this reason. Now, the opposite will happen here. Rather than introducing electrons between the two nuclei, now we are getting a condition where the electron density is absent between the two nuclei. That will result in a nodal plane because now there is no electron density between the two nuclei. We'll talk about this in detail when we will see the node and all. But for now, just understand it simply that in case of anti-bonding, the electrons are removed from the center and that results in a nodal plane. As a result, this will give more repulsion because now there is no shield between the two nuclei. And in turn, it will increase the energy and destabilize the molecule. Okay. Now, a very, very important point here, which is a point of important difference between the hybridization and the molecular orbital. And the point is law of conservation of energy. How can we understand it? Look here. If you look at psi A, it is having a higher energy than the sigma and a lower energy than the sigma star. So what you can say? The amount by which the energy is increased, the same amount is the one by which the energy is decreased. So the overall energy remains constant. Okay. The same amount, by the same amount, sigma is going down. And by that same amount or that same magnitude, the sigma star is going up. So that overall energy remains conserved. So you can say that the total energy of the two molecular orbital is equals to the energy of original atomic orbital. So before bonding and after bonding, the energy is same. Okay. Now let us move to the conditions for the combination of atomic orbital. If you have a doubt, you can ask it now. So let us move on to the conditions for combination of atomic orbitals. We have seen it right now that there is a linear combination. So the atomic orbitals are moving linearly and they are combining with each other. But moving linearly requires some special conditions which should be filled. Then and then only your two atomic orbitals which are coming linearly will combine, or else it will not combine. The first is they both should have almost the same energy, or you can say nearly the same energy. Suppose if you take the case of hydrogen, we were combining the 1s with 1s. It is difficult to combine a 1s of hydrogen with a 2s of hydrogen. Okay. And it is only true if you are considering homonuclear diatomic molecule like your H2. If you take a different molecule like your H2O or your HCl, which have two different type of atoms, then in that case, the conditions are quite complex. But for now, you can take a thumb rule. If you have a molecule made up of same two type of atoms, then you can always consider that only your two atomic orbitals will combine when they are of same energy. Okay. So 1s will combine with 1s, 2s will combine with 2s. Second is the most important point. Okay. So there may be a case that your atomic orbital with a somewhat different energy can combine. But it is never possible that your two atomic orbitals which are having different symmetry can combine. So they should have the same symmetry. Then and then only they will be able to combine. Now your question will be that what about symmetry? What is symmetry here? So that same symmetry is used here that you used in the case of overlap. Remember, we were combining the positive with positive and a negative with negative. Here also you have to follow that same thing. If you are combining two atomic orbitals, the same sign of the wave function should combine. Okay, so overall your electron is nothing but a kind of wave, a wave which is distributed like an atomic orbital, and that atomic orbital is represented by the wave function, and your wave function has positive and negative part, which is not the charge first of all, but it is your sine of wave function. Okay, so you can simply think it of as a coordinate, right? So suppose you can't be can't be in a negative distance, but you represent it in a coordinate with a negative sign. So that is representing just your position. Here also the same thing is applied. The positive and negative sign that you are seeing on the lobes of the atomic orbital, they are not representing the charge. They are just representing the phase. Okay, so positive is a phase and negative is a phase. Got it? And the combination will only take place when two same phases are combining. We'll see that. So, for example, if you are combining a 2pz, then you can only combine it with the other 2pz. Then and then only their symmetry will be same and it will result in a molecular orbital, or else it will not combine. So you can take the case of 2px and 2py. They will never combine with each other. Not in the case of homo or in the case of hetero. Both are not possible. So, if you want to build up a molecular orbital, you should satisfy these two conditions, and then only your atomic orbitals will combine up to a maximum extent. Means the atomic orbitals will overlap quite significantly. Then and then only your formation of molecular orbital will take place. So these three important points are there. So third point can be thought of as a result of the above 2 points: comparable energy and same symmetry. Then and then overlap will take place, and at last the overlap will be better. So that will result in a molecular orbital. Okay. Now these are the 3 points. Let us try to say implement this. So we'll see the implementation of this in the later on slides. So due to the implementation of these two things, various type of atomic orbitals are possible. What are those? Those are sigma, pi, delta. So multiple are possible. Okay, in the case of diatomic molecule. And to combine or to form this, what are the necessary conditions? If I short it down, they should have same energy. In case of diatomic molecule, which are homonuclear, I'm telling about those. Same energy, same symmetry, and decent overlap or better overlap. You can take any term. But in our discussion, we will be only focusing on two types of orbitals, molecular orbitals, and those are pi and sigma. We will talk about them in detail. Right? So I will tell you some very, very important point. Just listen it very carefully. Questions are asked from there, and it's quite difficult to solve them if you are not aware about the minute details in the formation of the molecular orbital. So student make a mistake of knowing only the electronic configuration of the MOT, or writing the MOT, or making the diagram. But the basics are important. You will be asked question in a competitive exam from this basics also. Okay. And if you are aware about this, you will have a first hand on the question paper. So first, let us talk about the sigma orbitals. How they are formed? They are formed by the, of course, head-on-head overlap. Same thing. And they are always symmetrical around the bond axis. Why I am saying that? For that, let us take the example of combination of two 1s orbital. Now, since it will be symmetrical around the axis, there will be combination of 1s and 1s to form two kinds of bonding orbitals, which are bonding and anti-bonding. So this is the diagram. It's very, very important to understand this diagram. Okay. There are two cases. In the first case, the 1s is combining with the another 1s to form the anti-bonding. In this case, they are combining in the opposite phase. Okay. And that is resulting in your anti-bonding part. So what we can say from this diagram? From this diagram, we can say that your bonding molecular orbital will look like this if the 1s of same symmetry is combining, and the anti-bonding will look like this. Now moving on further to the next type of sigma orbital, which is formed as a result of combination of 2pz. And again, since it is a sigma, it will be symmetrical around the axis. So you can see it here also, how it is happening. The positive and positive will overlap to form two kinds of bonding. In case of the bonding sigma molecular orbital, there will be no nodes. But in the case of anti-bonding, there is a node which is perpendicular to the internuclear axis again, similar to the sigma 1s. Okay? I hope you got the point, right? Which is pi orbital. Now, the important point about this pi orbital is that it is not symmetrical about the bond axis. Let us take the example of 2px to understand that. Suppose we have a 2px here. Okay. What will happen? The positive and positive will overlap, and it will give you two cases of bonding orbitals, which is bonding and anti-bonding. Okay. Now, these two atomic orbitals, which are combining to give you the bonding and anti-bonding, they will combine in the same phase. And there will be an internuclear axis in between. Similarly, here also there will be an internuclear axis. What about the nodal plane? So for the position of the nodal plane, there are two cases possible. If you take, in the case of the bonding one, there is only one nodal plane, which is along the internuclear axis, or you can tell it as that it is parallel to the internuclear axis. Whereas in the second case, if you consider, there are two nodes or nodal plane. What are those nodal planes? First is parallel to the internuclear axis, and second is perpendicular to the internuclear axis. So remember this. In the case of sigma, you have no nodes for the bonding condition. But in the case of pi, you have a node in the case of bonding condition. Again, moving on to the sigma, you have a node perpendicular to the internuclear axis in the case of sigma, in the case of anti-bonding. Whereas in the case of anti-bonding of pi orbital, you have two nodes. One is perpendicular and the second one is parallel. I hope this is clear to you. Okay. Now moving on to the next thing, which is level sequence of diatomic molecule. Now we know how to combine this diatomic molecule. Now let us see what is the outcome of this combination. So during the filling of bonding orbitals, we always keep in mind that the anti-bonding orbitals are filled first. Okay, now do not confuse this bonding orbital with the other part. Okay, so bonding orbitals are of two types, anti-bonding and bonding. So this anti-bonding orbitals are filled before. Okay. Next is, if I talk about the energy order of the oxygen and fluorine, then it looks like this. First is the formation of sigma 1s, which is from the two 1s orbitals that gives us sigma 1s and sigma star 1s. Similarly, if you take the two 2s orbital, then they will combine to form the sigma star 2s and sigma 2s. Okay. After that, we have the sigma 2pz, then type pi 2px and pi 2py, and then we have this. So this is only true for the molecule which is formed from the oxygen and from the atoms which are after oxygen. Whereas for the case of atoms which are forming the homonuclear diatomic molecule before oxygen, we have the different kind of order. What is that order? So we have sigma 1s, sigma star 1s, sigma 2s, sigma star 2x. But after that, instead of pi 2px, we instead of the sigma 2px, we have that pi 2px. Okay, clear? Then after that, we have the sigma 2pz. Is it clear to you? So it's very important to understand this. Now, let us try to see a whole of this in a single diagram. So this is your diagram. Before the B2, C2 and N2, which is boron molecule, carbon molecule and nitrogen molecule, we have the order of sigma 2s, sigma star 2s, then pi 2p, sigma 2p, pi star 2p and sigma star 2p. But after nitrogen, starting from the oxygen, we will have sigma 2s star. Okay. Then the order will change here a little bit. Okay. We will have sigma 2p, sigma 2pz. So this is the energy level diagram for the boron, carbon, nitrogen and oxygen, fluorine and neon. We will move on to the filling of electron later on, but you should understand it here that the reason for this change in configuration is due to the sp mixing. Now we will not go deeper into that. You should only remember the reason that for the case of boron, carbon and nitrogen, we have a different configuration with respect to oxygen, fluorine and neon is due to the sp mixing. So for boron, carbon, nitrogen, we have a sp mixing of 2s and 2p. Whereas for oxygen, fluorine and neon, we don't have sp mixing. Okay. Now we will move on to the results of the molecular orbital configuration. So what is molecular orbital configuration? Similar to the electronic configuration of atom, we have a configuration for the molecular orbitals as well, where your electrons are filled in different molecular orbitals. Okay. Then what about the stability? So we know that Nb represent the electrons which are present in bonding orbitals, whereas Na is the place where we are placing the electron in the anti-bonding. So remember this point always. If your electrons are more in the bonding case, then your molecule will be more stable because the bonding orbital are lower in energy. So you are filling electron in a lower energy, that will result in stabilization. Whereas in the case of filling the anti-molecular orbital more, you will see a unstable molecule because there is a greater effect of higher energy. Now moving on to the next. What is bond order? We have seen the bond order in terms of Lewis structure, but that is not accurate and not applicable to all of the molecules that we know. What it is? It is basically the difference between the electron in anti-bonding and bonding orbitals divided by 2. So we take the electrons in the bonding orbitals, right? Then we subtract the number of electrons from the anti-bonding and divide it by 2 to get the bond order. If the bond order is positive, the molecule will be formed. It will have a stable molecule. And if it is negative or 0, the molecule will not be formed and the molecule will be unstable. Next is the nature of bond. So we know that after counting the bond order, we will get different values. If the bond order is 1, it will have a single bond. If it is 2, we will have a double bond. If it is 3, we will have a triple bond. So as simple as that. What about the bond length? Now greater is the bond order, smaller will be the bond. And bond length decreases as the bond order is increasing. Last is your magnetic nature. So it's very important to understand this point. If you have all your molecular orbitals doubly occupied, then your molecule will be dimagnetic. Okay. And if it has singly occupied molecular orbital, then it will be paramagnetic. So if you see a molecular orbital diagram and it is a singly occupied orbital, then you will call it as the paramagnetic molecule. And if it has no unpaired electron, you will call it as dimagnetic. Okay, this was all for today's lecture. Thank you. So your math faculty will join you in a minute. Just wait for a while.